So in my previous video I've shown you how you can make a 12 volt to 24 volt DC to DC step up converter. I've also shown you how to make connections on breadboard in my previous video, but unfortunately there was a minute mistake. I forgot to ground one wire, so that was unfortunate, and thanks to Bronil for pointing that out, and in my previous video I've discussed in the comment section. So if you have any doubt, do check that out. So though my intention was to show you guys how you can make complex circuits on breadboards, so that not only this 12 volt to 24 volt boost converter, you can make whatever complex circuits you want to make on breadboard, but I shouldn't be doing that, so sorry for that. I'm also showing you the disadvantages and problem faced while making this project on breadboard, so you also know that I was making this project on a puff board. So today I'm going to discuss about it and show you the final result, and also show you some difficulties and problems faced by others, and also me, to actually help you to diagnose with that problem if you face it. So without wasting time, let's get started. So the first thing I'm going to talk about the components which are hard to get, and the first is the inductor. And in my first video of the introduction of this boost converter, I have told you that you need a Synths core and 60 turns of 22 gauge enamel coated copperware to make the inductor, but that was hard to get. You cannot get the Synths core in the market. So one thing you can do is just going to the computer repairing shops and tell them to give you the SMPS inductors. It's that simple. Okay, if you do not get Synths core, then you have to get some ferrite or carbon cores and just serve its purpose according to it. But the Synths core will be the best, but there is nothing to do if you cannot get it. So moving on to the next components, and that is the FR502 diode. Now let's go a little bit deep and understand why only FR502. So the first thing is it is rated 100 volts and whopping 5 amps. Now that means it can pass 100 volts through it, and it can also block 100 volts in the reverse bias. So that's the first point, and the second point is it has a low reverse current flow. And now think about our circuit. When our switch is closed, this diode is supposed to prevent the output capacitor from discharging. And now imagine if the reverse current flow of the diode is not low, then our output caps will be discharged and there will be no point using a diode anymore. So that's the second point. And the third point, and the most important point, the most important feature which the FR502 gives is it is fast recovery. Now what is fast recovery? So that is the topic for another video. It's quite a long topic, so I'm not going to discuss it in detail, but as of now, for brief understanding, you can understand it by something like we are dealing with higher switching frequencies here, so we need a fast recovery diode. So by understanding all these factors, the best alternative of this diode can be a Schottky diode, which features faster recoveries. So for example, you can get a 1N5822 diode which is rated 3 amps and have something kind of similar, which will actually fulfill our requirements in this project. So if you don't get FR502, don't get panicked, just get a Schottky diode which can be 1N5822. So the replacement components are listed in the description below as always. So that's gone for the hard to get components. Now I picked up a piece of perf board and soldered all the components in it, and after something around 2 hours of soldering, the project is completed. Now for the first test, I hook it up to a 12 volt adapter which offers a maximum of 1 amp of current to flow through it. And I do not use my bench power supply here because it can provide 16 amps, which can fry the whole thing up in just a second, as you cannot limit the current through it. So I've used a power adapter, which you can also buy cheaply, and it will also offer you a current limitation of something around 1 amps. So after hooking it up, you can see the voltage boosting to 20. Wait a minute. 35? That's not supposed to be. We don't need it. So as for the second test, voltages, you can see 1 means it is out of range, and it is showing out of range on my 200 volts range on my multimeter. And when pumping up the voltage to 600 volt, it's still sometimes showing out of range. Well, 12 volts to 600 volts. Are you freaking kidding me? Well, you can tell by just applying a little bit of common sense that it is fake, and it is not true, as our output caps were rated max 63 volts. They should pop right before 100 volts, and so this is fake info. And after digging a little bit, I figured out that is only the freaking loose connection what is happening between my multimeter and the output of the booster. So that's gone. For the fourth test, I plug a big LED with a 220 ohm 0.5 watt current limiting resistor, and right after plugging it, you can see our booster is not a booster anymore. It cannot even deliver current to light up a freaking LED? Let's find out. And look at the transistor terms going up like crazy. And this is the point I realized that I need a beefy heatsink to compensate such insane amount of heat coming out of it. Thus I used a thick long aluminum plate with a thermal compound in between. So now I decided to calibrate the output just after putting the heatsink in there through our potentiometers. But wait, I never succeeded in doing so. The voltage is jumping immediately to 30 plus volts, maybe a problem with the comparator. So I replaced the IC with a new one. That worked pretty fine. I'm now able to set the output to exactly 24 volts. Well, now let's see what happens with the load. Again, I put the previous LED with the same 220 ohm 0.5 watt current limiting resistor, and this time it got a little bit interesting. The temperature is quite stable now, as we have put a beefy heatsink in there. Our boost converter is able to do the magic up to 17.5 volts, and then it is collapsing to 13 volts. Now, to actually understand what is happening, let's listen to the switching frequency or the tone. Now, how? So, yes, through the coil wind. Now, what is a coil wind? Well, it is the vibrations in the winding of a coil. Less tighter windings produce a large wind, while a more tightly winded coil produces less noise. So basically, what you can do to reduce coil wind is to wind the cores tighter. So basically, mine is producing a very little noise, but I put my extremely sensitive microphones in there, and yes, now you can clearly listen the coil wind. And listen how the frequency is changing from 13 volts to 17 volts. And listen how the frequency changes from 13 volts to 17 volts, and again kind of dropping to 13 volts, and that is when our whole system is collapsing. So this is kind of tells that it cannot deliver steady current after 17 or 18 volts. So I replaced the 220 ohm resistor with a 1.2k resistor, and you can see the voltage is stable at 24 volts now. When measure the current through each of the resistor, you can see the clear difference. Through the 1.2K resistor, the current is something around 0.02 amps or 20 milliamps. But through the 220 ohm resistors, it's around 0.2 amps at the beginning and immediately dropping as before, 200 milliamps, and that made the difference. So plugging a DC motor in the outputs also shows the same issue. Thus, though we try to make a 12 volt to 24 volt booster, we ended up making a 12 volt to 17 volts booster. Maybe this is not the best boot converters you can build, or we did something wrong. Maybe we can figure out the problem and fix that by changing certain components, but I think I should end this project here. For prototype is just fine, and it can also keep a no load voltage of 25-26 volts easily. And you can also power some little LEDs with a 1.2K or higher resistor with it. Thus I removed all my testing jumper wires, soldered new wires, 2 LEDs for input and output, and raised the whole thing nicely. And again reinstalled the heatsink with thermal compound. And there we go. Now we can adjust the output voltage to be 24 volts. 24 volts, and the temperatures were still reaching more than 70 in less than 5 minutes. Try not to touch the heatsink, or else you will get a shock. Not electric shock, but a temperature shock. So there it is, guys. Hope you have liked it and hope it solves all your problems while making this booster. So basically, maybe I will make a new booster in the future. We can deliver more than 24 volts. I mean more than real 24 volts. Even you can plug in more loads with it. But as of now, I'm ending this project and hope you have liked it. Give it a thumbs up if you did, thumbs down for the opposite, and do share with your friends. And if you are not subscribed till, then do subscribe and hit the notification icon for getting updated in future. If you have any suggestions or any questions, leave in the comments below freely. I will reply to them within 24 hours. That's all for today. My name is Malhar. This is Out of Syllabus, and I'm signing off.